Welcome to our fourth learning workshop. We will be covering writing, balancing, and predicting the products of chemical equations today. So let's just jump right into it. So when we try to describe a chemical reaction, we write what's known as a chemical equation. We use the symbols of the elements to show what is reacting, and the things that are reacting are called reactants, and the things that are produced as a result of the reaction are called products. By convention, what you're going to see is that, by convention, you'll see that the reactants are always on the left side of the board. So reactants are always on the left, and you're always going to be reactants are going to be followed by an arrow, and the arrow goes towards products. So this is not an equal sign, this is an arrow. It's pointing towards something being produced. Because after the reaction occurs, the reactants are gone, the products are what are left. So products are going to be on your right side. Now, for many of us, it's going to be familiar, but if you happen to be from a culture that does not read from right or from left to right, this could be a little bit weird, but we're going left to right, reactants to products. All right, so we're going to go ahead and write and balance these chemical equations. So first of all, so we'll look at problem number 1. So aluminum, what is aluminum? What would I write for aluminum? Yeah, Al. So in this case, I'm just going to write Al. I'm just going to write aluminum. Now, it says and oxygen, so that means I'm going to do a plus sign because it's two separate substances, aluminum and oxygen. It's not aluminum oxide, it's two separate substances. What am I going to put for oxygen? Actually, not O. And it turns out,
O2.
O2, yes. It turns out there are roughly about 7 elements that, when they are by themselves in an elemental state, they do not exist as single atoms. They exist as diatomic molecules. And so here they are, and this nice little acronym you can use to kind of keep track of them. Brinkelhoff. So Brinkelhoff, Br, isobromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. So these 7 elements, when they're by themselves in their elemental state, they only exist as diatomic molecules. They do not exist as single atoms. So this would be O2. Now, it says it makes aluminum oxide. Okay, well, aluminum oxide, is that an ionic compound or covalent compound?
Is it ionic?
It is ionic. So that means we have to figure out what the charges are. What's the charge of aluminum? What's the charge of aluminum?
Is it -3?
Is it 3? 3?
Close. It's +3. But you had the number right. So it's, aluminum is going to be a 3 positive charge. And what's the charge of oxygen when it's part of an ionic compound?
2.
Yeah, it's 2 minus, right? So if aluminum's a 3 plus and oxygen's a 2 minus, what will be the formula then for aluminum oxide? Remember, we need to balance the charge. The total positive has to equal the total negative, right? What's the lowest common multiple of 3 and 2?
We need to balance it to be 6, 6 each, right?
Yeah, so I need a total charge of 6 positives and 6 negatives. So I need how many aluminums?
You need aluminum 2, aluminum I need I
And you
need
need how
three.
much?
You need three oxygen.
Very good, very good. So you got aluminum Al2O3. I need the lowest common multiple of 3 and 2 is 6, so I need a total positive charge of 6 and a total negative charge of 6 to make the balanced ionic compound. Okay, so now that I have the equation written, now I can go ahead and balance it. And when you're balancing it, a lot of times the easiest thing to do, and I'm actually going to see if I can select this. Select. Yes. Ooh, whoops. Question? Go ahead.
Yes. How did you get Al2 and O3? Like, why is the
That's a very good question. So basically what it comes down to is this. So I have, if I have aluminum, which is a 3 plus, and I have oxygen, which is a 2 minus, I need these to balance, okay? So I look for what is the lowest common multiple of 3 and 2. So what's a multiple of 3? Well, that's just counting by 3. So it's 3, 6, 9, etc. And then same thing with oxygen. 2, 4, 6, 8. I'm counting by 2 since it has a charge of 2. But here's the thing. With an ionic compound, I'm looking for the empirical formula, the lowest ratio that's going to give me balanced charge. I need the charge to be balanced. I need the total number of positives to be equal to the total number of negatives. Now, if they were already equal, if it was a plus 3 and a minus 3, I would just do 1 and 1. But since they're not already equal, I have to figure out what the lowest combination I can use to get so that they have the have an equal charge. So the lowest common multiple you can see is actually 6. That's the lowest multiple they both have. So to get 6, I would need 2 aluminums, because 2 times 3 gives me a positive 6. To get 6 with a negative 2 from oxygen, I need 3 oxygens, because 3 times negative 2 gives me negative 6. So that's why I get Al2O3. And you'll notice, kind of interestingly here, is that this is the second multiple of aluminum, which means you need 2 aluminums, and it's the third multiple of oxygen, so that means you need 3 oxygens. Does that make sense?
yes, thank you.
Yeah, you're welcome. Okay, good question, good question. So now we have to balance the equation. And to balance the equation, we're going to want to list out, what I usually like to do is list out our elements. So I'm going to actually take our equation here, and I'm actually going to move my sheet over so that I can focus on the equation itself. The Al2 plus O2 goes to form Al2O3. And so what we're going to do is list out the we're going to list out the elements. So I'm going to list out my elements here, and I only have 2 elements, so this is going to be a little bit easier of a one for us to balance. So I have aluminum and I have oxygen. Now, truthfully speaking, you don't actually have to list out your elements if you don't want to, but I found that the easiest way for students when they're first starting to balance equations to get the hang of it is to list out your elements, because if you try to balance it in your head, especially for the more complicated ones, you're gonna go a little crazy. It's gonna mess with your mind. Um, so the first thing I do is I do a little chemical accounting. I'm trying to figure out how much of each atom I have on each side. So how many aluminums do I have on the left side, the reactant side? Thought I heard somebody say something. How many aluminums do I have on the left side?
1,
1. Very good. And how many oxygens do I have on the left
2,
side? Very good. So I have 1 oxygen, or 1 aluminum, 2 oxygens. How many aluminums do I have on the product side? Yeah, 2. Now, how many oxygens in the product side?
3.
Yep. So I'm going to go ahead and balance these. Now, usually you want to balance whatever is easiest to balance first. Now, the easiest element to balance is typically going to be the element that is present in the fewest places. In this case, both of them are equally easy to balance because, for example, aluminum is only present in 2 compounds, and alternatively, oxygen is only present in 2 compounds. So it's going to be equally easy to balance either one. So let's go ahead and balance aluminum. Now when we balance, we can't change subscripts. We can't change the little numbers on bottom here. We can only change coefficients. The coefficients are the numbers in front of the element. And those coefficients are multipliers. They multiply how much you have. So I have 2 on the left side, or on the right side for aluminum, and only 1 on the left side. So I'm going to go ahead and multiply this by 2. Actually, I'm going to change that color, make it a little darker so it's easier to see. This is going to be 2. So 2 aluminums. Okay. Well, if I put a 2 in front of there, that means I have to show that down here. So this is now 2. All right, aluminum is balanced. However, now my oxygen is not balanced, and I have to balance that. Well, here I have a little bit of a problem. I have a 2 here and a 3 here. I have an odd with an even. Whenever you're trying to balance an odd number with an even number, you're going to have to double the odd to make it even and then rebalance. Because I can't multiply 2 by any whole number to get 3, right? So double the odd to make it even. So double the coefficient of the compound that has an odd number of oxygen. In this case, double it means I put a 2 in front of the Al2O3, right? So now this is going to multiply everything in this compound. It's going to multiply the aluminums, and it's going to multiply the oxygens. So how many aluminums do I have now on the right side?
4.
4. And how many oxygens do I have?
6.
6. So what you might notice is that the aluminums have now become unbalanced on the other side. So what do I need to change the coefficient of aluminum on the left side to? What should I put in front of aluminum on the left side? And 4
4.
on the right. Yep, change it to a 4. Exactly. So this is going to be a 4. Change this to 4. Now aluminum's balanced. Now I can balance the oxygens. I have 6 on the right hand side and 2 on the left hand side. What do I put in front of the oxygen to balance it? Very good. Good job, Monica. That's a 3. Yep. I'm going to balance it by putting a 3 in front of the oxygen. And so now I have a balanced equation because 3 times 2 is going to give me 6. And now the oxygens are the same and the aluminums are the same. So this is the balanced equation. Not too bad, right? Maybe a little challenging.
I'm confused though.
What can I what's confusing you? What can I help with?
No, why I said I'm confused is because at first you had put just the Al plus O2 and we got Al2O2 or 203.
Al2O3. Yeah.
Then all of a sudden now you changed everything to 4Al. So is it that you changed the whole formula that we were working with before or what?
Well, not exactly. No. See, here's the thing. This is okay. So let me use this. Okay, this is the compound that's formed. Al2O3 is the compound that's formed, and I do start with O2 oxygen. Oh, hi, Tiana. Yes, they are so cute. Sorry.
I don't understand. Okay.
But yes, So this is aluminum is the reactant and O2 is the reactant. But see, the numbers in front tell me how many of these that I need in order to react to form the product on the other side. So the coefficient tells you how many, and what I've squared or circled, tells me what are the substances. So, like for example, if I was reacting with ozone, ozone is O3 actually, it's the other elemental form of oxygen. So if I had O3, this would be a different this would be a different equation. It would end up balancing differently um, if I used ozone to make aluminum oxide. And this would actually be an even more reactive substance. But anyway, it would end up being this, because 2 aluminums plus 1 O3 gives you Al2O3. So this this tells me what is the substance, and then the number in front tells me how many of that substance that you need in order to make the product. Does that make sense?
I think it will get some time to. It will take some time to get used to it. But the thing is,
Yeah.
this from the aluminium you're talking about right now. It does it just produce only one product? Because, for instance, they can give you this aluminium with this would give you this product. Is it only one product that aluminium give you, which is what you just did now, or is it that
Mm,
when you
yeah.
give us the formula? Who's
So
that?
in the presence of oxygen, yes. In the presence of oxygen, aluminum is only going to give you one product. Um,
What's that?
if
Aluminum
you have
oxide.
Yeah, aluminum oxide. If you have an extremely high temperature and you have the presence of nitrogen as well, then aluminum will also react with the nitrogen and you'll also get aluminum nitride. So it kind of depends on what is present. But as far as aluminum and oxygen, when they react together, they will only form aluminum oxide. They won't form anything else. And what I said to you before, what I said to you about the substance is kind of important because, like, ozone is present in the upper layer of the atmosphere, but it's also present in the ground layers, like in the layer that we breathe, because of pollution. And ozone is extremely reactive. This is a very reactive and relatively dangerous molecule. And I say dangerous because if you breathe in ozone, if you breathe in O3, it will oxidize your lungs. It will damage your lung tissue. Okay, so it's not good to breathe in. This is why you have these red days in Texas, where it's like, don't go outside, or orange days, like unhealthy air, don't be outside. The reason it's unhealthy is because there's a lot of ozone, and ozone can oxidize your lungs, and it's damaging it, and it hurts you. Oxygen is a completely different gas. We depend on it for life. We need it. We need it to breathe in. And if you have a high level of oxygen, it actually is not bad for you. It um, actually helps you feel a little bit more invigorated if you have a high level of O2. But these are two very different chemicals. And so when I write the equation this way and I balance it this way, um, I'm representing a very different reaction than if I write it this way and balance it this way. So it's the substance is indicated, the subscripts kind of tell you what compound it actually is. This is your compound product, this is your compound reactant, this is your reactant compound. But it's the coefficient, just the big numbers in front, they just tell you how many of each one you need, or how many of each one is produced. I don't know if that helps too much, but I hope it does. I hope it helps a little bit. Any other questions?
Are we working it? Okay, how are we doing it? Is it because I know that normally they will tell you that I've seen question in chapter 6 assignment that says, okay, this one, how many ions are in this? How many? What is the element? What is the symbol? What is the formula? And I know they're all different questions. So if we work like that, I think we'll understand it better.
Okay.
Hmm.
Well, so yeah, I mean, I think what's almost more helpful is to ask what is the substance. if it gives you a reaction description, what is the substance you're dealing with? Because a substance can either be an element or a compound.
Okay.
And if it's an element, that means it's in its elemental state by itself. And if it's a compound, it means it's two or more elements combined together. But yes, we'll continue. We'll work some more and we'll break it down. And I hope that will make it a little bit clearer. Let's go ahead and I want to actually do another practice question. Let me go ahead and erase this extra stuff. So I'm going to erase this and this. So the next one is this is kind of a fun one too. Um, Sodium hydroxide and hydrogen sulfate produce sodium sulfate and hydrogen hydroxide. So in this case, we're dealing with all compounds, no elements. So sodium hydroxide, is that an ionic compound or a covalent compound? Yeah, ionic. Very good, Tierney. So, yep, we're going to go ahead and have to figure out the ion. Sodium is what? Na, and what's the charge? The charge of sodium. Remember, you can tell from the periodic table.
Plus.
Plus 1. Very good. So sodium's a plus 1, or just plus. And then hydroxide, that's one of those polyatomic ions that you're supposed to have memorized, right? What's OH? Oh, well, I said what it was. But yeah, hydroxide is OH. So oxygen and hydrogen with an overall charge of -1. So those two things together, it's a plus 1 and a minus 1. So that means that the formula is just going to be NaOH. I'll go ahead and write that down. NaOH. Okay. Then it says and hydrogen sulfate, so and for the H there. Now the interesting thing about hydrogen is that hydrogen tends to act like hydrogen tends to act like a metal in many cases. So you can almost, even though it's technically speaking a covalent compound, you can kind of treat it like an ionic compound if hydrogen is the first one listed. Which means hydrogen, if it has a charge, hydrogen would have what charge?
+1.
Plus 1. And sulfate is a polyatomic ion. Do you remember what the charge of that one, what that one is? It's not 3. What is sulfate? It is -2. What is sulfate? Sulfur combined with 4 oxygen. So sulfate is SO4 with a 2- charge. In actuality, what it is, sulfate is a covalent compound that is a charged covalent compound. That's what all the polyatomic ions are. They're basically charged covalent compounds that combine with metal sometimes form ionic compounds. Okay, so if H is a +1 and sulfate is a 2-, how many H's do I need for this formula for hydrogen sulfate? What's the formula going to be? If I want the charges to be equal, the positive charge has to equal the negative charge. Yeah, I need 2 hydrogens, and I need how many sulfates? How many SO4s? 2 SO4s would give me a negative, or a total -4 charge. But I want with my 2 hydrogens, that only gives me a +2.
4.
No, 4 sulfates will give me a -8 charge.
But this but the oxygen also has 8. That's 4 and 2. That's
And
8.
you can't look at it because remember, the SO4 is a covalent compound.
Oh,
It's a
okay.
charged covalent compound. So you can't look at the individual charges of the sulfur and the oxygen. You have to look at it as a polyatomic ion. Its overall charge is -2. So there are 2 hydrogens, he said. Well, 2 hydrogens would give me a +2 charge. Well, that means I need a -2 charge. So I need how much sulfate? How many sulfates?
No sulfate.
Well, no sulfates would be 0, but I just need 1, right? Because if I have a +2 from the hydrogens, I just need a -2 from the sulfate, right? So I'll just need 1 sulfate. Or to put it in other terms, so you could let's do that whole table that I did. If that helps you see it, what's the lowest common multiple of 1 and 2? This is 1, 2, 3, etc. And this is 2, 4, 6. The lowest common multiple is 2, which means I need how many hydrogens? I need 2. It's the second multiple. I need how many sulfates? I need 1. It's the first multiple that gives me the 2. Does that make sense? 2 hydrogens, 1 sulfate. 1 sulfate. Okay. So I'll go ahead and erase that, and then just go ahead and put my hydrogen sulfate here.
At what point do they put parentheses
Parentheses.
when you have
You
the O4 and the 2 minus? Is that supposed to be parentheses there or something?
you would use a parentheses if you have more than 1 polyatomic ion. If you have more than 1 sulfate. If I only have 1 sulfate, which I can actually see that I do only have 1 sulfate that I need here, then I would not use a polyatomic ion. Or I would not use parentheses rather. If I
Okay.
only have 1 polyatomic ion, I don't use parentheses. If I have 2 or more, then I would.
Okay.
And it says this produces, so I have hydrogen sulfate, sodium hydroxide produces sodium sulfate, the next compound, and hydrogen hydroxide, also known as water.
Hydrogen
So,
hydroxide is water.
yeah, I mean, strictly speaking, nobody would ever call water hydrogen hydroxide. Um, I mean, you could technically call it dihydrogen monoxide if you wanted to, but dihydrogen monoxide is the same thing as water, and people just commonly refer to it as water. So sodium has a +1 charge, right? And sulfate we know has a -2. So what would the formula for sodium sulfate be? I heard it in the background. What's the formula for sodium sulfate?
NaSO3.
Not SO3.
SO3 minus? No, sorry.
Okay. Well, okay. So maybe so let's look at we'll do that chart again. Um, the sodium is a +1 charge, and sulfate, remember, is SO4 2 minus, right? Not SO3.
Sorry.
So what's the lowest common multiple of 1 and 2? What's the lowest common multiple of 1 and 2?
2.
2. So how many sodiums do you need?
2.
I need 2 sodiums. How many sulfates do you need?
1.
It's Na2SO4. And then plus water. And water, of course, is H2O. Okay. So now when I'm balancing this can get a little tricky because you might notice that hydrogen appears in 3 different compounds and oxygen appears in all 4. So this could get a little bit tricky. I'm going to go ahead and erase some of this unnecessary stuff, but just so I have a little bit more room to work with. All right, and I'm going to move my little worksheet over for a second. So here's my equation. I need to balance it now. So what I'm going to do here is list out my elements. Yeah, I'll use this. Okay, so I'm going to list out my elements. I have sodium, oxygen, hydrogen, and sulfur. And I have the same elements on the other side. I have sodium, oxygen, hydrogen, and sulfur. Okay, sodium is Na, sorry. So then I'm going to count up how much of each one I have on each side. And I have one. How many sodiums on the left side?
One.
One. How many oxygens?
Two. 5.
5. I have to look at the both substances. I have 5. How many hydrogens do I have on the left side?
3.
3. Remember, it's 2 different places. How many sulfurs do I have?
1.
1. How many sodiums do I have on the right side?
2.
Yeah, 2. How many oxygens do I have on the right side?
1. No, 5.
5. There we go. How many hydrogens do I have?
2.
Uh-huh. And how many sulfurs?
1.
1. Okay. So I have. Now at this point, I'm going to want to balance whatever is easiest to balance first. And here's where that rule comes in. The easiest thing to balance is going to be the thing that appears the fewest places, in the fewest places, or rather specifically in the fewest substances. Now each one of these is a substance, a different compound, so to speak. The substance can be either an element or a compound. So I have 4 substances in this equation. How many substances does sodium appear in?
Say it again.
How many substances is sodium in?
2.
Yeah, it's in this one, and it's in this one. It's only in 2.
Mm-hmm.
How many substances is oxygen appear in? In this whole equation?
4.
4. Yeah, it's in every single one.
Mm-hmm.
So 4. That's going to be the hardest to balance. What about hydrogen? How many places does that appear in?
3.
1, 2, 3. Yep, 3 places. And what about sulfur? How many places does that appear in?
2.
2. Only 2 substances. Okay, so it looks like I'm going to want to balance sodium and sulfur first, then hydrogen, and then oxygen. Now sodium is not balanced. I have 1 on the left side, 2 on the right. So what do I need to do?
Make them to be make both of them to be 4.
Well, I don't want to make them both be 4. I want to balance in the lowest whole number ratio possible. Keep in mind, these coefficients, these numbers in front, they're multipliers. Yeah, Leanne mentioned it. I add 2 to the left. Coefficients are multipliers. They multiply in front of it. So if I want to get the 1 to be the same as the 2 on the other side, I have to multiply the 1 by 2.
Okay.
So 2 times 1 sodium, that gives me a total of 2 now.
2. Okay.
And 2, I also have to multiply times the oxygen. So how many oxygens do I have now?
That would be 7.
Not 7.
No, 10. Sorry. 10.
Not 10.
Is it not 2 times? No. Is it on just the left side?
It only multiplies the substance that the coefficient is in front of. So you see that plus sign?
So
It's not going to multiply it's not going to multiply anything past that plus
you had
sign.
three oxygen.
Mm-hmm. So
You had 1. You have 2 oxygen now.
2.
So this 2 multiplies this,
That 1.
this, and this It doesn't multiply anything over here.
Okay.
So that means I have 2 oxygens from this compound, and I have 4 from this compound. So that's a total of, yeah, 6.
I'm as confused as hell.
Do you see where I'm getting the 6?
I'm confused.
2 times 1 oxygen there. And then you also have to add the 4 from the other compound.
Are you
Any
adding
questions?
the two to where you have the plus, right? The other
Yeah,
H2SO4. Are you adding that to, are you
yeah,
multiplying this two with that
yeah.
one
So
too?
these are, no, I don't multiply that because this 2 is not in front of that. Just like, for example, if I had 2x plus 5y,
Mm-hmm.
I wouldn't say that I have 10y, right? I
That's what
don't
I'm
have
saying.
10.
So how did you get 6 oxygen? Where did 6 come from?
Because I have 2 times 1 oxygen for I have 2 NaOHs, right? So there's 2 NaOHs, so there's 2 sodiums, 2 oxygens, and 2 hydrogens. But I also have the H2SO4 over here, which has 4 oxygens. So I take
So that's the question I asked you just now. Does this 2 also multiply across the addition sign? Does it
and
go
I
to the
said no,
H2SO4?
and I said no, no, it does
So
not.
how, yeah. So,
It doesn't multiply across, but you still have to add the oxygens from both sources.
So the 2 in front of the NaOH, that means sodium is 2, oxygen is 2, and hydrogen is 2, plus
Exactly,
the 4 oxygens over here, which makes 6.
exactly, exactly. There's 4 oxygens here, plus there's 2 from the NaOH, the 2 NaOH. So that gives you a total of 6. So what about hydrogens? How many hydrogens do you have now?
4.
4,
4.
4.
I have 2 times the 1 here plus the 2 from the H2SO4, so that gives me a
Mm-hmm.
total of 4. So yes,
Mm-hmm.
absolutely, very good. You have to keep in mind that this number, this coefficient, doesn't multiply whatever's down here. It multiplies whatever's in front of it. So, I know some people were automatically saying there's 10 oxygens because I put a 2 there, but it doesn't multiply all the oxygens. It just multiplies the oxygens from the compound that it's in front of. All right, cool. Well, now I've balanced sodium. Now I can balance my next element, sulfur. But fortunately, sulfur is already balanced, right? 1 and 1. So I'm still good with that. So I go to the next hardest element to balance, hydrogen. I have a 4 here and a 2 here. So what do I need to do?
Added 2, 2.
Yeah, I put a 2 in front of H2O, right? So that's going to multiply the hydrogen. It's going to multiply the oxygen. So how many hydrogens do I have on the right-hand side now?
4.
4. And how many oxygens do I have on the right-hand side?
2.
6.
6. So 2 from the water, because there's 2 waters, and 4 from the SO4, from the Na2SO4. So that is going to be a total of 6 oxygen. And now you'll notice something interesting. By balancing the easier elements first, oxygen balanced itself. Notice that oxygen is now balanced without me having to do anything. So that's the best, that's the easiest way to deal with these. Balance the easiest elements first, and then the hard ones will balance themselves. Okay.
Oh boy.
So kind of in a nutshell, you take your problem and you break it down to this, like the simplest form, I guess, and then balance it from there.
Exactly. Yeah, so when you're balancing the equations, you only change the coefficients. You cannot change the subscripts when you're balancing the equation. All right, so I'm going to go ahead and erase some of the work here. And I want to show you another another challenging problem. But then after that, I want to start looking at predicting products because I think that'll also be helpful to you.
So what's the final answer?
That is the final answer. 2NaOH plus H2SO4 goes to form Na2SO4 and 2 waters. And I know this seems intimidating right now. I know this seems intimidating, but you're going to get to the point where it's only going to take you a few seconds to balance an equation like this,
I
because
pray.
you're gonna get better with practice, but you are going to need to practice with it. It's not something that's going to necessarily be obvious right away, but you'll get there. Everybody starts out slow with this, so don't feel bad if you're not picking it up super fast right away. This is not easy. Balancing equations is kind of challenging. So um, I want to go ahead and give you a couple of a little bit more challenging ones. I think that will be helpful. Um, okay, so the next one that I'm going to do is actually it's called combustion. It's a combustion reaction. It's not one of these here, but I want to do one of these because you're going to most certainly get one of these from your professor, and it's probably about the hardest type of balancing equation question you can get. So let's say you have something like this: C2H6 plus O2 goes to form CO2 and H2O. If I'm balancing something like this, once again, the first thing I want to do is list out my elements: carbon, hydrogen, oxygen. And on the same side, or on the other side, same thing: carbon, hydrogen, and oxygen. And when you're listing out your elements, make sure you list them out in the same order. It'll allow you to keep track of these a lot easier. So, because my carbon's right across from the carbon here, hydrogen's right across from the hydrogen, oxygen's right across from the oxygen. So how many carbons do I have on the reactant side, the left side?
2,
Hmm. How many hydrogens?
6,
Hmm. And how many oxygens do we have on the left side?
2.
Hmm. And how many carbons on the right side?
1,
1.
And how many hydrogens?
2,
2.
Good. And how many oxygens?
3.
3. Very good. Because you have to recognize that oxygen's present in 2 compounds. You add them up, that gives you a total of 3. Okay, so here's the deal. At this point, I want to balance whatever's easiest to balance first. And you'll notice, if you look at carbon, carbon's present in only 2 places, right? It's present in the CO2, and it's present in the C2H6. You'll also notice that hydrogen is present in 2 places. The
Michael,
C2H6.
is somebody watching television? It's loud.
Yeah, sorry. So yeah, if you have noise in the background, if you don't mind turning off your mic when you're, I want you to participate, but whoever that is, regardless, it doesn't matter. But we want you definitely to participate, so you can unmute yourself to answer. But if you have a lot of background noise, yeah, just maybe just silence it when you're not responding. Thank you, appreciate it. Okay, so hydrogen is only present in 2 places, but how many substances is oxygen present in this equation?
3.
3. It's present in O2, CO2, and H2O. So this is going to be the hardest. The other 2 are pretty easy. They're only present in 2 places. But oxygen is going to be the hardest one to balance. I want to balance that last. So let's start with the carbon. Balance element by element. So there's 2 carbons on the left side, 1 on the right side. What do I do?
You add 2 to the 1 on the right hand side, I think.
Well, you're not wrong, but it's going to be 2 in front of what?
2 in front of the carbon.
2 in front of the carbon, this carbon? Or do you mean the carbon dioxide?
No, not the carbon dioxide, the carbon itself.
Oh, no, no.
No.
You
Of
have
the
to put it,
CO2.
yeah, you have to put it in front of the carbon
CO2, yeah.
dioxide,
Okay, yeah.
not the carbon. This is just for this down here, this is all just for keeping track. That doesn't help you balance the equation, or that's not going to, you don't want to put anything in front of these guys. Uh, you're trying to figure out what coefficients go in front of the substances, the different compounds. So yes, I'll put a 2 in front of CO2, but that's going to change my carbon. And how much carbon do I have now on the right side?
3,
Not 3,
2.
2. Very good. And how much hydrogen, or rather, now it also changed, this changed the carbon, but it also changed the oxygen. So how much oxygen do I have now on the right-hand side?
5.
5. Very good. Yeah, because I have to multiply that 2 times 2, that gives me 4, plus the 1 from the oxygen is going to give me a total of 5. Hydrogen was not affected because there's no hydrogen in this compound. Okay, so next, I'm going to balance my hydrogen. I have 6 on the left, 2 on the right. What do I have to do?
You add 4 to the one on the right.
I don't add, remember. These coefficients are not adding anything. They're multipliers.
Oh, sorry.
So what do I multiply? So what do
3.
I have to multiply it by 3.
3.
Exactly. So I have to multiply this by 3. That's going to multiply this, and it's also going to multiply this. So how much hydrogen do I have on the right-hand side now?
6.
6. And how many oxygens do I have on the right-hand side now?
3.
Not 3. How many total oxygens on the right-hand side?
4. No. 4.
Not 4.
How
6.
many? Okay, sorry, but this other side, sorry.
It's not 5. It's not
6.
5 or 6.
6.
Not 5 or 6. So look at the CO2. How many oxygens are in the 2 CO2s?
You had 4 there. 4 plus
There's
this
4.
other 3. That
And then
is
there's
4
3
times 3,
from the
that's 12.
water. So how many? No. So there's 4 from the CO2, and there's 3 from the water.
That's
So
7.
that's 7. Exactly. So it requires you to be a little careful with your thinking here, because it's very easy to make mistakes in tallying these up.
Yeah,
Okay.
instead of me to add, I'm multiplying.
Yeah.
Oh, jeez.
All right. So now I have a problem. I have an odd number of oxygens on the right-hand side and an even number of oxygens on the left-hand side. What do I do?
You have to balance the oxygen on this or this on this left-hand side. So
Yeah. But the problem is I can only use whole numbers. I can't use fractions to balance chemical equations. So if I have an odd number I'm trying to balance with an even number, do you remember what you do?
you put a parenthesis.
You have to think Vegas, double the odds. Double the odds.
Double the odds.
Yep, double the odds. So double the odd number to make it even. So if you have oxygen on the right-hand side of 7 and oxygen on the left-hand side of 2, which side has the odd number of oxygen?
It's the right-hand side, the 7.
The right-hand side. And which compound is causing the number of oxygens to be odd? The CO2 or the H2O? Which one of
The
those has an odd number of oxygen?
The H2O.
The water. So I have to double the 3. I have to double the 3, and that's going to turn to a what?
4.
Double 3 is not 4.
6.
6. So there's going to be 6 waters now. And now it
Whoa.
means I have how many hydrogens?
6.
Not 6. No, there's 2 hydrogens in the formula, and this is
Oh
a
no.
multiplier.
6,
12,
8.
yeah.
12.
12.
God.
Remember, coefficients are multipliers. They multiply.
Okay.
All right. Now, how many oxygens do I have total now?
6, 7, 6, 9, 6, 8.
8.
8. I have 4 from the CO2. Well, actually, not 8. I have 4 from the CO2, right? The
Oh
2
yeah.
CO2, so that gives me 4
That's
oxygens.
10.
And then
10.
I have 6, yep, 6 from the water, so now I have 10. 4 plus 6 is 10. So this is now 10 oxygen. Unfortunately, I could try to balance oxygen here, but it wouldn't necessarily be the best idea because remember I want to save oxygen for last, and by doubling the water here, I've now unbalanced hydrogen. So I have to rebalance hydrogen before I balance oxygen. So I have 12 hydrogens over on the right hand side, but I only have 6 on the left. What do I have to do?
Put a 2 in front of the hydrogen.
You got it. Put a 2 in front of the C2H6, right?
Mm-hmm.
So that's
That's
going to
gonna throw
multiply.
out the. Okay, no, don't gonna try.
Yeah, that's going to multiply the carbon and the hydrogen. So I have how many carbons on the left-hand side now? 4. And I have how many hydrogens?
12.
Very good. Very good. 12. So 4 carbons, 12 hydrogens. All right, so am I good to balance oxygen, or do I have to do something else first?
We need to go back and balance the carbon.
Very good. We have to balance the carbon now. So there's 4 on the left-hand side, 4 on the reactant side, 2 on the right-hand side. What do I do? Add, but remember, it's a multiplier. What do I need to multiply?
Put a subscript to the C to make it 2.
Nope, I can't change subscripts. That changes the compound. I can't do that. I'm
Oh, sorry.
balancing the equation.
Okay,
So I'm
make
going
it
to,
4.
Change the
I
2
can make it
into a
4.
4.
Exactly. I can make the 2 into a 4. I just have to multiply by 2. Exactly. So I'll change that to a 4. And now that's going to give me,
Gonna throw out the oxygen then.
uh-huh.
Gonna
And
throw out
so
the oxygen again.
I have 4 carbons. And now how many total oxygens do I have?
14.
14. 4 times 2 is 8 from the CO2, plus 6 times 1. 8 plus 6 is 14. All right, now I have an even number of oxygens and an odd number of oxygens. I can balance this. I mean, an even number of oxygens on both sides. I have 14 on the right-hand side, 2 on the left-hand side. What do I put in front of the O2? Very good. 7. Excellent. 7 times 2 gives me 14. I am now balanced.
That's a lot of work. Jeez.
And this is most likely the hardest type of balancing problem you are likely to get.
I hope she will not give us something like this in the exam.
Uh, she almost certainly will.
What?
I'm not kidding. They will have you balance at least 1 or 2 of these combustion problems on the exam. So you will want to practice this definitely. Um, it once you get the hang of it, it's not too hard, but it does require a significant amount of practice. Fortunately, there's a lot of practice up on our website with this. All right, so let's go ahead and switch gears. We're going to go to predicting the products. Okay, I'm gonna go to predicting the products. So I'm going to add a new sheet here. Um, predicting products. Where is it? Where's my predicting product? Ah, here we go. Bam. Oh, and also, I want to share with you a really cool thing. Uh, Notes on balancing equations. So this is kind of a step-by-step guide slash handout for balancing equations. If you need to kind of remind yourself, you go ahead and click on that and download that, or save it or print it. So how to balance any chemical equation. It lists the steps, lists out your elements, determine what to balance first, balance the easiest element first, changing coefficients, not subscripts.
Michael, are you going to send this to our email? Would
Uh,
you, please?
this is the same that notes on balancing equations. This is the same one that I sent in the email with the link. You can either download it from that, or you can click on that link there. But
You sent both files, both of them?
yeah, all the files. I did send all the files. I did send all the files to you. Ah, here we go. I'm gonna make this super big and fatty. Okay. So I want to go through the different types of reactions you can see, and how to identify them, and then we'll do some practice with it. So synthesis or combination, called both. Synthesis reaction is essentially the simplest type of reaction, usually involving two elements, where two elements, or it could be an element in a compound or two compounds even, combine to form a single product. But usually it's like two or more elements combined to form a single product. Anytime you see only elements on the reactant side, chances are you have a synthesis reaction. The generic form of this is A plus B goes to form AB. Okay. An example, an actual example would be like, for example, what we did, that aluminum plus oxygen, O2, goes to form Al2O3. Remember that reaction we balanced at the very beginning? And this is 2 aluminum oxides, 3 oxygen, and 4 aluminum. That would be like the balanced equation. But this is just an example of a synthesis reaction. Notice that the key factor here, the key thing to notice is it's always only one product. So one product. So a synthesis reaction always has only one product. Okay? Next. The next type of reaction is the opposite of a synthesis. This is a decomposition. Decomposition reaction. And in a decomposition reaction, you get a breakdown. It breaks down. Instead of being A plus B goes to form AB, you get AB breaks down to form A and B. Sometimes it's just a compound breaking down back into its elements, and sometimes it's a compound breaking down into an element in a compound, or two compounds. But the key thing to note here with a decomposition reaction is that there's always only one product, or always only one reactant rather. Only one reactant. So a synthesis has only one product. A decomposition reaction has only one reactant. And an example of a decomposition reaction might be something like this. It might have something like this. You might have like magnesium carbonate and that might decompose to magnesium oxide and CO2. Or you could have something a little bit simpler. You could have um, AL, I don't want AL, I want AG. I'm trying to keep these reactions that I know happen, like real reactions. I guess it's not that important, but AlCl will break apart into, or AgCl, silver chloride, using photography, it'll break apart into silver metal and chlorine gas. So this would be like 2, 2. So these are examples of decomposition. Decomposition, and you have synthesis. All right, so let's do the next one category would be what's known as a single replacement reaction. This is a single replacement, sometimes called single displacement. And a single replacement or single displacement reaction is basically what happens when you have a compound reacting with an element, and the element will switch places with one of the elements in the compound to give a new compound. So you might get AB plus C goes to form AC plus B, or alternatively, you might get AB plus C goes to form CB plus A. And the key thing to recognize if it's going to be a single replacement reaction is that it's always going to be an element and a compound. So you can tell just looking at the reactants, okay? With the synthesis, it's usually, these are just usually elements. So this is kind of like an important giveaway that it's going to be a synthesis, is that usually it's just only elements. Whoops. Only elements that are in are reactants. And with decomposition, it's pretty easy because it's always only one reactant. So that's easy to spot. And then with a single replacement, basically, you're always going to get one element and a compound reacting together. And it will form a new element and a new compound. And the principle of a single replacement reaction, like the basic idea behind it, is that like replaces like. What does that mean? Like replaces like. It means that if your element is a metal, like for example, if C here is a metal, it's going to change places with A, which is a metal. So if C is a metal, it changes places with A. That would be like, for example, here. So if C is a metal, it'll change places with A, which if A is a metal. If C is a nonmetal and B is a nonmetal, then they're going to switch places. C is going to take the place of B, and B is going to come out by itself, which is what you see happen here. But like replaces like. The element that's by itself will switch out for what is like unto itself. So if it's a metal, it'll swap places with the metal. The nonmetal, it'll swap places with the nonmetal. Okay. Next, let's do double replacement or double displacement, depending upon your professor. And with the double replacement reaction, the interesting thing with this is that the reason you can tell that this is going to be a double replacement reaction if you're looking at the reactant is that you always get this two compounds reacting. And typically it's two ionic compounds, so that AB plus CD goes to form AD plus CD. Because remember, when you have an ionic compound, the metal is always listed first, and the nonmetal is always listed second. So these could be polyatomic ions, and they could switch places, etc. But yeah, this is a double replacement reaction. So you can always tell a double replacement reaction because there's going to be two compounds reacting, usually ionic. And an example of a double replacement reaction is like the one that we actually did up here, NaOH and the H2SO4. That was actually a double replacement reaction because the sodium switched places with the hydrogen. Now, when I say like replaces like, and I said metal replaces metal, non-metal replaces non-metal, actually really it'd be more appropriate to say positive charge switches places with positive charge, and negative charge switches places with negative charge. And so let me actually go ahead and type that out here as just kind of a little bit of an emphasis here. Um, I'll just do this. So this is positive charge switches with positive charge. Or positive ion switches places with positive ion. Negative ion switches with a negative ion. It's the charge that matters, not necessarily so much whether or not it's um, a metal or a non-metal. All right.
When
So
you
then,
say when you
go
say
ahead.
an ion, what is an ion?
An ion is a charged particle. So anytime you like see sodium Na plus or magnesium Mg2 plus or O2 minus, any charged particle is an ion. And you can have single atom ions like I mentioned, Al3 plus O2 minus, or you could have polyatomic ions, which are basically multi-atom ions. So essentially they're covalent compounds that have an overall charge, like sulfate SO4 2 minus or hydroxide OH minus. You know those 8 polyatomic ions you're supposed to memorize? Those are all those would be considered ions as well. But yeah, an ion just means a charged particle. All right, so that's single replacement and double replacement. Um, Actually, I'm going to draw a big fat box around each one of these. So, double replacement likewise follows the like replaces like rule. Double replacement likewise follows the like replaces like. Like replaces like. Okay, and just for clarity's sake, I'm going to go ahead and put big boxes around each of my different reaction categories. Just because I feel like I put these a little too close together, and I don't want you to be confused. Confusion's bad. By the way, I hope you all were able to get through the whole storm without too much trouble this past week. It was really, really crazy. There's a lot of people who are really hurting. All right, and then synthesis. All right, synthesis, decomposition, single replacement, and double replacement. Okay, and then lastly, there's combustion. So combustion reactions are probably the easiest ones to recognize. A combustion reaction.
I would have preferred it if you were using elements to represent instead of this A, B plus C, D. If you can be using elements instead, it's better.
Well, so let me go ahead and give an example. The double replacement reaction, I'll do a single replacement reaction example. So here's an example of a single replacement. So this would be something like, we'll do this, Mg plus AgCl goes to form MgCl2 and QAG. And I'll put 2 in front of AgCl. So that's an example of a single. See, in this case, magnesium, which is a metal or will become a positive ion, it's going to switch places with silver, which is also a metal. So they'll switch places, and the magnesium will go with chlorine, and the silver will come out. Now, it is important to note here that when they switch places, you have to rebalance it. When it switches places, you have to rebalance it based on the charge. So magnesium as an element has a 2 plus charge. So when I put it together with chlorine, I have to rebalance it. So chlorine only has a -1 charge, so I have to put 2 chlorines for every 1 magnesium. And then likewise, I'll do another example for the double replacement reaction. So here's an example for this one. So let's say you had, I'll do this. So I have PB NO3 2. So lead 2 nitrate plus aluminum chloride. And that's going to form PbCl2 and aluminum nitrate. And once again, you need to notice that you're actually, well, this isn't balanced as it is. I'll have to balance it. So change these coefficients. This is actually going to be 3, a 2, a 3, and a 2. Basically, the idea here is that, once again, like replaces like, so the metals are positive charge, the Pb2 plus and the Al3 plus, they're going to switch places. But when they switch places, aluminum is going to go with nitrate, yes, but I have to put them back together according to their charges. Nitrate's a -1, aluminum's a +3, so that's why this is AlNO3 3. It's not AlNO3 2 like lead was. And when lead goes with chlorine, I don't put PbCl3 because the aluminum had 3 chlorines. Lead is a 2 plus charge here, so it's going to be PbCl2. When I put them back together, I have to put them back together according to their charges. But yes, like replaces like. That's the principle. All right. And so now I'm going to go ahead and put a big circle around this one as well. All right. So now we have combustion. Now we have combustion. So here's our combustion. This is the last type that you need to know. And for combustion, it's actually really simple. It's some sort of a hydrocarbon, so CXHY, and X and Y can be any number, plus oxygen goes to form carbon dioxide and water. Hydrocarbon and oxygen goes to form carbon dioxide and water. And that's it. Those are the 5 different types of reactions: synthesis, decomposition, single replacement, double replacement, and combustion. Combustion always has the same 2 products. It's always carbon dioxide and water. Now sometimes you can sometimes have oxygen with the CXHY. It might have also oxygen or 2 there. But anytime you have a carbon-hydrogen compound with oxygen, you know it's going to be combustion. And this is kind of like the one that we just did, the one that we just did together up here. This was a combustion, C2H6 plus oxygen goes to form carbon dioxide and water. That's an example of a combustion reaction. So any questions on any of that? You want, does anybody have any questions? Okay. All right, so does anybody want to go through a couple examples of practice with regards to predicting the products and identifying what type of reaction they are? All right, let's do it. So for this one, let's start with the first one. Hydrogen and oxygen. So if I'm looking at this, hydrogen and oxygen. Well, hydrogen is just an element, right? So what should I put for hydrogen?
H.
I'm sorry?
H2.
H?
H plus.
So
H
how,
plus.
there's actually a hydrogen. Remember, when anytime you have an element in its elemental state, do you remember what we have to remember these guys? Hydrogen is a
H2.
Binkelhoff element. Yeah, this is
Give us
it's
H2 plus
it's
O2.
H2. H2 plus O2.
Mm-hmm.
So based on that, I see that these are 2 elements. What type of reaction is this going to have to be? Synthesis, decomposition, single replacement, double replacement, or combustion? What type of reaction would this be?
Synthesis.
Yeah, it's not double replacement because Double replacement requires you to have two compounds. I think Linda, did you say it?
I said synthesis.
It is a synthesis. Yep. Two elements combining. This is going to be a synthesis. So this is a synthesis reaction, and it's going to combine to form one single product. Okay. So hydrogen, what's the charge of hydrogen when it's part of an ionic compound? I know this is covalent, but we're going to just assume.
What did you say again?
What charge does hydrogen tend to have? Remember, hydrogen tends to act with the metals.
Plus.
Yeah, hydrogen's going to be a +1, right?
Mm.
What charge does oxygen tend to have?
Minus.
-2, right?
2
A 2
minus.
minus. So if hydrogen's a +1 and oxygen's a 2 minus, what's the formula for our product? A very familiar formula.
2H.
2HO or H2O?
H2O, sorry.
There you go. Yeah, the H2O. It's water. And then you could go ahead and balance it from there. All right, so let's take a look at the next one. Aluminum sulfide and then an arrow. Well, aluminum sulfide, is that an ionic compound or a covalent compound?
Covalent.
It's not covalent.
It's not. I don't even know the difference. That's the truth.
Oh, you were here for our ionic versus covalent workshop. And this was 2 weeks ago, though. So
That was 2 weeks ago. I actually brought some questions for us to refresh on last week before, so we don't forget, because I totally forgot when I had no water and light. I totally forgot about every other thing about school.
Oh, I completely understand that. Okay. Well, basically, yes. Ionic compounds are when you have a metal and a nonmetal, and covalent compounds are when you only have nonmetals. Okay.
Covalent nonmetals.
So ionic metal and a nonmetal, covalent only nonmetals.
Ionic is, you say it's metal and non-metal?
One metal, a metal and a nonmetal. So
Okay.
basically if it has a metal, it's ionic. If you have a compound and it has a metal, it's ionic. So if all of it is nonmetals, then probably it's covalent. Okay, so given that this is aluminum sulfide, is aluminum a metal or a nonmetal?
Aluminum is a metal.
And then sulfur is a metal or a nonmetal?
Non-metal.
So you have a metal and a nonmetal, so is it ionic or covalent?
Is it ionic?
It's ionic.
Mm.
Very good. So this is ionic. We have an ionic compound here, which means I have to look at the charges. What's the charge of aluminum?
Al3.
3 plus, good. And what's the charge of sulfur? This is sulfide, not sulfate. So this is not a polyatomic
Sulfide
ion.
is O2.
Well, no, there's no oxygen. Sulfide.
Sorry, sulfide will be S2 minus.
S is a 2 minus charge, exactly. So aluminum's a +3, sulfur's a 2 minus. So what's the formula for aluminum sulfide?
Al2, 2Al, or Al2, Al23. No, Al2, S3.
There you go, Al2S3. Very good, very good. So here is our aluminum sulfide, and it reacts. So what type of reaction is this going to be? If aluminum sulfide is my only reactant, what type of reaction is this going to be? You can either type it in the chat or turn on your mic if you want. What type of reaction is this going to be? Aluminum sulfide reacts.
Decomposition?
You said it, but you said it quietly.
Huh?
I can't hear you. Your mic is
Is it a decomposition?
It's decomposition. Very good. Absolutely. It's a decomposition reaction. And so if it's a decomposition, that means it's just going to break down into its elements. That means it's just going to go to aluminum and sulfur. Now, is aluminum a Brinkelhoff element?
What?
Is aluminum or sulfur one of these guys, the Brinkelhoff elements?
No.
No. So in that case, I can just write Al and S. And then balancing at that is super easy. I just put 2 in front of Al and a 3 in front of S. Put 2 aluminum atoms and 3 sulfur atoms. Very good. Now, let's skip ahead. Let's do sodium sulfate and calcium chloride. So sodium sulfate. And just to speed things up just a little bit, because I know we're running out of time and some people have to go. Sodium's a +1 charge. And sulfate, remember, is SO4 with a 2- charge. So this is going to be Na2SO4 because I need the +2 to balance with the -2. So I need 2 +1 sodiums and 1 -2 sulfate. And then likewise with calcium chloride, calcium is Ca with a 2+,
2+.
and chlorine is Cl with a 1-. And so I'm going to need 2 chlorines to balance with the 2 sulfurs, or 2 +2 calcium. So it'll be calcium CaCl2, because the lowest common multiple of 1 and 2 is 2. I need 1 calcium to get a +2, and 2 chlorines to get a -2. And then from there, all I have to do is single replacement. Now here's the cool thing. Since you've already done all the work of, well, I did all the work for you actually. Just kidding. Now, since you already did all the work of figuring out the ions, you have a positive here. When I switch them, I know that, okay, so sodium is going to go with what element? When I switch them, well, first of all, actually, what type of reaction is this? Because before I do anything, I have to figure out what type of reaction this is. I have 2 ionic compounds, so what type of reaction is this?
Sulfur will go to calcium. Calcium,
Two,
sulfur.
2 ionic compounds, what type of reaction is this? Double, very good. Double replacement reaction. Right on, Krista. So, this is a double replacement reaction, which means I have to switch the ions. So, what is sodium going to go with? I'm going to switch out sodium.
Sodium chloride.
What element is going to go with chlorine? So, sodium is going to switch places with calcium, and it's going to go with chlorine. It switches places with calcium, but sodium is going to go with chlorine. And when I put them together, I have to put them together according to their charges. Well, sodium is a +1 charge, right? And calcium has a -1 charge. So if sodium is a +1 and calcium is a -1, what's the formula for sodium chloride?
Sodium chloride is 2 minus.
Well, sodium is a +1, chlorine's a -1. So if I put them together, what is the formula? Now I just need one of each.
What is Cl2 minus is what?
Well, no, there is no Cl2-. Chlorine is a 1- charge.
Oh, sorry, -1.
And sodium's a +1 charge. So sodium's a +1, chlorine's a -1. They're already balanced. I just need one of each. So it's just sodium chloride. Does that make sense?
Yes.
Okay. So now, what's the other compound that forms?
Calcium sulfide.
Calcium sulfate. And what's the
Sulfate.
formula? Calcium's 2+ charge. Sulfate's a 2- charge. So what's the formula? What's the chemical formula?
Calcium sulfate.
Yep, very good. It's CaSO4. 1 calcium and 1 sulfate. I only need one of each because they have the same equal and opposite charges. Very good. And then if I balance this, I just need a 2 in front of the chlorine. But there you go. Yeah, this is a double replacement reaction. This is a double replacement reaction. And this is a synthesis, a decomposition, and a double replacement. And now we can do a real easy one, number 6, C6H14 plus oxygen. Well, C6H14 is just C6H14. Oxygen is going to be what? What am I going to write for oxygen?
No.
Sorry,
It's
everybody
oxygen,
can't
not
hear.
O2.
O2, there you go. O2, very good. And then, what are the products going to be? Because this is what type of reaction?
Carbon hydroxide.
What type of reaction is this, though?
Mm.
Very good, Leanne. It's a combustion reaction. It's a combustion reaction. And since it's a combustion reaction, the products are always the same. What are the products? They are? What are the products of a combustion reaction always?
Calcium hydroxide.
It's right there under combustion. What are the products of a combustion reaction? CO2 and H2O. Very good. So CO2 and H2O, carbon dioxide and water. That's the easy. Then you just have to balance them. Very good. And let's just do one more before we call it. We have magnesium, which is Mg, and I have hydrogen chloride. So hydrogen's a +1, chlorine's a -1, so that'll just be HCl. Hydrogen tends to act like a metal, even though it's a nonmetal. And what type of reaction is this? Where I have an element and a compound. What type of reaction is this? What do you think, gang?
Single replacement.
Single replacement, very good. It's a single replacement reaction. So, since it's a single replacement reaction, like replaces like, hydrogen has a positive charge. What charge would magnesium have if it's part of an ionic compound?
3+.
I think you said it, but I couldn't hear you.
3+. I don't know why you cannot hear me. I don't know why.
Well, I don't know. Yeah, I'm not sure. Like,
I think magnesium comes with a 3+.
not a 3+.
All right, 3+.
A 2+. Yeah. So magnesium would actually have a 2+ charge. And so magnesium is going to have to, what are the products going to be? Magnesium is going to have to go with what element on the product side? Is magnesium going to combine with hydrogen, or is it going to combine with chlorine? Yeah, it's going to combine with chlorine. It's going to switch places with hydrogen, right? Because magnesium and hydrogen are similar. They're both positive charges. They're going to switch places. So hydrogen's going to go by itself. Magnesium's going to come in. And if magnesium comes in with chlorine, magnesium has a 2+ charge, chlorine has a 1- charge. What's the formula for magnesium chloride? Mg has a 2+. Chlorine is a -1. I need the charges to be equal.
MgCl.
What'd you say?
Mg2. No. Mg2Cl. No.
Lowest common multiple of 2 and 1 is? Lowest common multiple is 2. So how many magnesiums do I need?
I think you just need that magnesium, but you need to balance the chlorine to be.
Yeah, I just need 1 magnesium, and how many chlorines do I need?
You need 2.
I need 1 magnesium to get a 2+ charge. How many chlorines do I need to get a 2 charge?
2 chlorine.
I need 2 chlorines. Exactly. So this is going to be MgCl2. MgCl2. And then, of course, hydrogen's going to kind of go off by itself, right? Hydrogen's going to go off by itself. But see, if hydrogen goes off by itself, how do I write that? What am I going to write here?
Hydrogen is 2, right?
Did I write it just H?
2.
H2, very good. Exactly, because it's a Brinkerhoff element, right? It doesn't exist by itself as just an H. It's an H2. Doesn't like to be alone. All right, cool.
It'll be lonely.
Awesome. Well, excellent. Well, I hope that was helpful for you. And of course, this I would just want to balance. If I was going to balance this, I'd just put 2 in front of the HCl, and that would do it. But I hope that was helpful. Make sure that you take some time to practice these because and there's a lot of practice available for you up on our website. In fact, let me go ahead and share my screen with you. I want to show you all the practice problems we have. So I'm going to go ahead and stop sharing this, and I'm going to share my entire screen. And you can see that in addition to the stuff that I sent you by email, the answer keys for both of these practice problem sets are here, and you can see that they're completely worked out. You can check yourself. You can try them on your own, and then you can check and see how if you can do it. And there's some combustion problems here, and some other problems here that will be helpful. You super cute girl. Hold on just a second. Daddy's almost done. And then of course we also have up on our main chemistry web resources page practice problems here. And if you look at the chemical reactions and quantities, there's balancing equations, writing and balancing equations, predicting products, mixed predicting products. There's a lot of different balancing equations practice. Cutie, I love you. Oh, don't be sad. All right. You smell like chocolate. Were you eating chocolate? Were you eating chocolate?
I was thinking if we could just go through some questions before we go.
Oh, sure. What question would you like to go over?
Yeah, I just previous ones.
I'll share a whiteboard. Go ahead and you can write on a whiteboard. You can write your question.
Ouch. How do I? Okay. How do I write to that one?
Click on the pencil icon. It's on the top of the screen. Click on the pencil icon, and then you can write on the whiteboard.
Okay. Let's do this. Okay.
Button down if you write on it.
Okay. This is what we have done before. It's it says oh, this is gonna take forever. Can I just type it in the other box there?
Yeah, you can type it in the box, or you could just tell me what it is.
Okay, yes, I can tell you. That's better. Formula of ionic compounds.
Okay.
Yeah, you have the name is sodium chloride.
Oh, okay.
Okay, no, leave that one. Let's do calcium phosphide.
Calcium
phosphide. Yeah.
Phosphate or phosphide?
Calcium phosphide.
Phosphide,
right?
like this?
Yes, phosphide. Okay, you have the positive ion is Ca plus, right?
Yep, Ca2 plus.
The negative ion is P. Is that P minus?
P, what's the charge? Not 1 minus, it's
the negative ion is what? P minus?
P with a 3 minus charge.
Is it P3 minus?
Because you look at where it is on the periodic table, and what's the closest noble gas to phosphorus? Look at the argon, and if you see that the argon has the 18 electrons, and phosphorus has only 15 electrons. So phosphorus is going to have to gain 3 electrons to be like argon. So that's why it's a -3 charge. Does that make sense?
Yes. So what would that be? Would that not be? So how would that be Ca What is the formula for this now? What's the formula?
Well, you do the lowest common multiple. What's the lowest common multiple of 2 and 3?
6.
6. So how many calciums do you need to get a total charge of 6?
3.
3. And how many phosphoruses do you need to get a total charge of 6?
You need 2.
2.
I got the chocolate.
You got a
So
chocolate? Oh, good girl.
does it mean that anytime how would I say it now? Whenever you find the common multiple, you write it at the bottom, right?
Uh, you can write the lowest common multiple if you want. You don't have to, but the bottom line is that the total positive charge has to be equal to the total negative charge. So, like for
Okay.
example, if you want to kind of draw that little table, like the way that I showed you, this is just to help you if you have trouble doing it in your head. You can draw like this and be like, okay, what is the multiple of 3? It's going to be 3, 6, 9, etc. What are the multiples of 2? It's going to be 2, 4, 6,
Yeah.
etc. And then be like, okay, well, the lowest one they have in common is 6. So how many calciums do I need? I need 3 of
3.
them. How many
Yeah.
phosphoruses do I need? I need 2 of them.
2. Okay.
And
So
so,
that's it. This is the formula now to be calcium phosphide, right?
exactly, that's calcium phosphide,
Okay.
Ca3.
Okay. What about rubidium sulfide?
Rubidium sulfide.
Mm-hmm.
So
The
rubidium,
positive ion will be what? Rb
so
plus?
rubidium has what charge?
Rubidium, I
Plus
don't know.
plus 1,
Plus
plus 2.
rubidium, I don't. Plus 2? I
Is it
don't
in the
know.
first? Is it in the first column or the second column?
Is it rubidium sulfide?
Yes, but is rubidium in the first column on the periodic table or the second column on the periodic table?
Let me see. Oh, where's my? Let me look for my.
You always want to have your periodic table out when you're doing these
Right.
problems.
Okay. Let me see. Let me look for it. I have it here. Rubidium. Oh, I saw it just now. 1 minute. Sorry.
Hmm.
Yeah, I'm trying to refresh my head. Okay, rubidium is I don't know. Is it no? This is not rubidium. Sorry. It's
No, it's there.
RB, right? RB.
Uh,
RB is 1A.
yeah. So here's the periodic table. Yeah, rubidium here has 37, and it's 37. And it's in the first column. And
Yes.
so if you look at it and you compare it to where's the closest noble gas to rubidium, well, this is a 37. Closest noble gas is 36. So rubidium is going to want to lose an electron. That's 37. To go from 37 to 36, you have to lose an electron. That's
Mhm.
the hedgehog. 37 to 36, so you lose one electron.
Mhm.
And if you lose an electron, you're going to be positively charged.
Okay.
So rubidium is a positive 1 charge, and sulfur is going to be a 2 minus charge because you look over here at sulfur, and it's 16, argon is 18, so it's going to gain 2 electrons to be like argon, so it'll be a negative 2. And so then if I go ahead and then write those down, rubidium is Rb with a plus 1, and sulfide is S with a 2 minus charge.
You need to write it. You need to write that one. You need to write that one, or just write plus.
You could just write plus if you want to. You don't have to have the 1.
Yeah.
Um, the plus, if you just see a plus, the 1 is assumed. But yes, so rubidium's a plus 1, sulfur is a 2 minus. What do you do?
So the
What's the lowest
formula would
common?
be what? The formula would be RB 2S RB 2S. Is that it?
RB2S, exactly. 2 rubidiums, 1 sulfur, and then you'll have balanced charges. That's
All right.
correct.
Okay. What about aluminium bromide?
Uh, so aluminum bromide, right? So uh, you got me using the British spelling. Aluminium bromide.
Yeah, the positive ion is aluminum is 3 plus, right?
Yep, it is 3 plus, and bromine is what? Bromide is what? Oh, whoops. I don't know what I'm doing.
Am I supposed to write? Okay, when they say what is the positive ion, do I say 3 plus or I just say plus?
Well, the positive ion would be 3 plus.
Okay, 3 plus. Okay, then the negative ion for bromide would be minus bromide.
And
Is
yeah,
bromide
bromine
minus
is
2?
it's
2 minus?
not 2 minus, because remember, bromine's right next to that noble gas. Bromine's right next to the noble gas. So it's just, it only needs to gain 1 electron, right?
So that's
Bromine's just,
1.
yeah, it's going to be a -1, because
Just
bromine has
minus,
a,
right?
yeah, because bromine was 35 electrons, and it wants to be like krypton, which has 36. So it's going to gain 1 electron, and therefore it'll be a -1.
You need to write the minus 1. That's 1 minus I does.
Or 1 minus. You can write you can write, and honestly, professors aren't too picky. Like when it comes to like if you write 1 minus or -1, or if you just write a minus, you really don't need the 1. You can just write
Yeah,
minus.
I think I'm just okay, just put just minus. BR minus.
Uh-huh. And so if aluminum's
Yeah,
a 3 plus and bromine's a -1, what would the
yeah.
formula be?
The
How would
formula
you,
would be AL uh hold on. AL this is a little bit tricky. AL ALBR3. Is
exactly, ALBR3.
that correct?
That's correct.
Hey, okay.
Very well. And
Okay,
what's the,
ALBR3. Oh,
mm-hmm,
the 3 goes to the bottom. Okay,
mm-hmm.
AL3. AL3.
Yeah, 'cause you
Okay,
always have
let's
to
do it. We have a potassium selenide.
potassium selenide. Okay, well,
Mm-hmm.
potassium, what's the charge of
K,
potassium?
K
Potassium's a
plus,
K.
K2 plus,
K plus, 1 plus, did you say 2 plus or 1 plus?
1 plus.
1 plus, very good. And then selenide is selenium, that's Se. What's the charge of selenide?
Selenide. Se 2 plus,
Mm-hmm.
2 plus.
Yep, you got it.
Okay, so this will not be K K2 K2 Se.
Yep, K2Se.
Is that correct?
That's correct, very good.
Okay,
You
good.
got it. You're on a roll.
Barium oxide.
Barium oxide. This will probably be the last one I can do because I need to get back to the main tutoring room. But you could
Okay.
definitely feel free to come and visit me if you
Yes,
want to
I
go
am.
over some more.
Would you be chanced?
Yeah, yeah,
Okay,
I'll be
let's do
available in the main room. So barium is what charge?
Barium is 2 plus.
2 plus.
Is that it?
Yep, and then oxygen is what?
Oxygen is 2 plus. 2,
2
no,
plus.
sorry, minus. 2
2 minus.
minus.
So in this case, they're balanced. So what's the formula?
AO. BAO.
There you go, BAO.
Okay.
Excellent.
Okay, I think I'll come and visit you well, how long are you going to be there?
I'll be here until 8 o'clock tonight. But
8? Oh,
yeah,
okay, I'm going to come there. Let me just rush and do some
no
deliveries.
problem. Well, thank you everybody for coming to our session. Hope that was helpful.
Everybody has gone.
Yeah, I know.
Only
This is for the video. This is for the video. Thank you
okay.
everybody for coming. Thank you for coming, and I hope you have a great week. And we'll see you next week. Bye.
Thank you. Okay.